All right. So now that we've done a lot of work with computing limits, we want to get back to sort of the whole reason we went down this road. Um, I think I said before that there's two branches of calculus. There's the differential calculus and the integral calculus. Both of those, to actually achieve it, you start with basic algebraic or geometric properties, and then we apply a limiting process to it. We take the limit of something. And that's what we're going to do here. And that's what, back in the average rate of change video, we did this one about shrinking the interval. And here you can see the results of that, right? This was the position function, the height function of something. And we were trying to narrow down what the exact velocity at t equals 1 was. And what we did was we took this interval where one of the ends was 1, and we kept making it shorter and shorter, right? Smaller and smaller. Here it was 1 second, then half a second, then a tenth, hundredth, thousandth, 10,000th, and so on. And what we're doing is shrinking the interval. Now, if we follow the trend of numbers here, we can try and make an intelligent guess as to what the actual outcome might be. Well, of course, we want to be able to know for 100% certain what this sort of limit is, right? This is a limiting process here. The limit that we're doing here, okay, which is what we call the instantaneous rate of change. So instantaneous rate of change. All right. What we're doing here is we're essentially computing the limit as delta t goes to 0 of delta h over delta t. This is what we want to do. So delta t is the difference between 1 and or between the left and right numbers here, right? We're shrinking that down. Right? This limit, what this essentially ends up being, the way we compute it, is the limit here. It's so h of 1 minus h of, let's call it t, over 1 minus t. And here it's the limit as t is approaching 1. Right? So if we look at this left number here and call it t, right? The right number is always 1. If we call the left number t, this number is approaching 1. So we're taking the limit as t approaches 1 of this expression right here. Right? And this expression right here is the average rate of change. But we're going to take the limit of that now. So let's go ahead and do this. The limit t goes to 1. Let's plug in 1. That'll be 20. And then minus 36t minus 16t squared. Okay, all this is over 1 minus t. So what we need to do is try and factor the top of this if we can. Right? So let's organize this a little better. Limit as t goes to 1. 16t squared. Let's see, I can factor a 4 out of this, so I'm going to go ahead and do that now. So this is 4 times 4t squared minus 9t plus 5. And then 1 minus t. Right, so let's continue this limit computation over here. Limit as t approaches 1. Let's see, can we factor this? I hope so. One of these is going to be a 5. One of these is going to be a 1, if we can factor it. Let's see. So if we do 4t minus 5 and then t minus 1, this should work out. All right, excellent. It does. All right. So now that we have this limit, notice that this factor and this factor will cancel each other out and leave a -1 behind. So let's do that. Put a -1 here, 1 here. So this will be limit as t approaches 1 of, this is -4, 4t minus 5. All right, and now we just plug in t equals 1. -4 times 4 minus 5, and we get 4. Right, this limit is just equal to 4. As we sort of were expecting, right? If you remember from when we did this problem before, we looked at these numbers and said, okay, they're trending toward 4. Here, we actually verify that it's trending toward 4. Okay? So this instantaneous rate of change that we computed here, this is what we call the velocity. Right? So when you have a position function, the instantaneous rate of change is the velocity. Right? So another way we could compute this is, maybe I'll say alternatively, the instantaneous rate of change, limit, as delta t goes to 0, of delta h over delta t. Another way we could have computed this is taking the limit as h goes to 0 of, oh, shouldn't use h twice, huh? Let's call it a. This would be t plus a minus h of, I'll leave the t here over a. So this t here should be whatever value you're trying to compute the rate of change at, or the instantaneous rate of change. Okay. So hopefully that makes sense there, and we'll talk some more about this a bit later.